let me now kick things off and talk about caching strategies. So in this talk, let's discuss some of the common caching strategies that exist, as well as some of the typical trade-offs involved in each. Next, I will do a deep dive into ScyllaDB's cache design and try to answer some questions as to why we implemented our own caching layer, how it fundamentally works, as well as go through some of its available features. So, first and foremost, which strategies exist? Plenty. And although you will find that that's something I mentioned in the lounge, I'm a very opinionated person on my own. The reality is that there is no single better or worse way for you to cache things. Of course, there are recommended patterns you should follow up on and requirements which might make one of the strategies we are discussing less relevant as opposed to others. But at the end of the day, you should always think about the problem you are solving so you can come up with the ideal topology for your caching workloads. Therefore, in this talk, I won't touch much on the use case side of things, which is something Alan and I saved to go later in our presentations. So this is a chart that I stole from ByteByteGo, which pretty much sums it up. Allow me to do a quick free advertisement for them and tell you that if you do not follow those guys yet, maybe you should, because they very often post interesting articles related to distributed systems and high performance design. All right. So the first strategy we are going to see is basically cache aside, where your application looks up data in the cache, and in case a miss happens, it will fall back to your database. It will then retrieve the data and update your cache. In a nutshell, that's how it works. The next one is read through, where instead of your application going to the database and populating data, the cache will automatically do it whenever a miss happens. Here, we eliminate the application complexity of, going to the cache, waiting for a miss, go to the database, and then populate the cache. But the latency is still driven by the time it takes to round the trip to the external database, populate the cache, and service back your request. Next, we have write through, where all of your writes go to the cache, and it synchronously writes to the database. And here, your latency, your write latency, is driven by your database, given that every write happens synchronously. And down in the left, I'm pointing to my screen. You guys cannot see it. Sorry. Down in the left, we have write around, where you write primarily to the database and read from the cache, but fall back to the database and update your cache or your database occasionally. And finally, we have write back, where your application writes to the cache constantly, and the cache will update your database asynchronously. Here, the main drawback is that the failure of your caching layer may result in data loss, and sometimes you can tolerate it, but sometimes you cannot. Now, let's see how some implementations actually manifest in practice. Let's start with perhaps the most common pattern seen out there, which is cache aside. In this strategy, most of the work is actually handled by your application. Your cache and your database are basically treated as separate entities, and it is your responsibility to maintain consistency when it's needed, as well as dealing with things like cache invalidations and so forth. In a nutshell, a read comes in, you check whether the data you're after exists in the cache, and as I said, in case it doesn't, you'll then go to your database. As an example of a write-through cache, and someone mentioned about the DynamoDB accelerator in the lounge. DynamoDB accelerator is an example of write-through cache, or DEX, as it's also called. And DEX is the sort of cache that sits in front of your database, in front of DynamoDB, and every write to perform is synchronized with Dynamo. One aspect that may happen in this strategy is that if a user directly updates the underlying DynamoDB table, without going through your DEX. Um, and the item in question is not yet considered stale or evicted from your cache, then your subsequent reads from your cache are going to become inconsistent. And this is very similar to the complexity raised on cache-aside workloads, where you need to handle cache invalidation. So whenever you are using a strategy like this, you must have well-defined contracts with your application developers whenever writes or updates are done outside your cache. And although writing to DynamoDB Accelerator alone should generally be performant, the fact is, as I said, it is synchronous. And because it's synchronous, it might affect your tail latencies negatively. Think about it this way. If you have a Zipfian-like pattern where writes get concentrated over a few popular keys, such as posts in going viral in a social network, and imagine a ton of users concurrently liking that post, something like that, then DynamoDB Accelerator is not going to do any sort of coalescing to you. And this is something you will need to still figure out on your application and ensure you update your cache in fewer hops to avoid the impact of all those synchronized requests eventually hitting your database and the prevent Dynamo from eventually throttling you down. So DynamoDB Accelerator is by definition mainly a write-through cache. However, you could also use it as a read-through one. And this is because if you require strongly consistent reads for every read request you do through DEX, then it will directly route this read to its underlying DynamoDB table so it can fetch the data you're after. And this gives you some layer of flexibility, but keep in mind that depending on how you use it, it might simply kill the purpose of caching in the first place. For example, if every write is synchronous and every read you do is strongly consistent, then you probably don't need a cache because you are basically synchronizing every operation with your database. Therefore, what I said up front is always define well-established contracts in your application for writes and ensure that most of your eventually consistent reads never become stale if your use case cannot tolerate that. Thus far, none of the strategies we discussed really addressed the problems involving cache consistency as you write. And this is this is where write around or write back, which are different strategies, try to provide some answers. The trade-off between those two strategies drill down to either latency or consistency. That is, in a write back pattern, you tolerate a period of time when your database is not up to date. Sometimes that's fine, sometimes it is not. It's up for you as a business to decide. And there's a risk window on which, if your cache fails, you may permanently lost all those unsynchronized writes. On the other hand, write around simply writes directly to your database first, which ensures that your data is consistent, and then leaves the cache invalidation logic down to you. Finally, we get to only read through, which is the strategy used by ScyllaDB. It is worth highlighting here that unlike all previous other strategies, ScyllaDB's cache is not an external component that you place in front of your database, aside of it, or anything like that. Rather, it is actually embedded and is shipped along with the database. Read through is extremely simple to reason about. Caches are, as you know, often read mostly components in your infrastructure. And as you read, a miss indicates that the database needs to go to the underlying data store to fetch the data, whereas a hit means that this request can get serviced immediately. If you are using an external read-through cache, then you would probably also want to come up with a proper write strategy, such as the one we have seen in DEX, for example. But because ScyllaDB's cache is embedded, you don't need to really worry about writes by any means. So naturally, it just brings me to the second part of my presentation, where I will now shift to discuss how ScyllaDB's cache design works. Uh, but before we actually talk about our caching specifics, it is important to understand why ScyllaDB, or maybe even why other databases need / implement a cache in the first place. To do that, let's understand in ScyllaDB how a write occurs. In ScyllaDB, a write to be considered successful needs to be stored in two places. First is the main table, which is an in-memory data structure that accumulates your writes over time. And second, it also needs to be stored in the commit log. And the commit log is basically a write-ahead log to ensure durability and consistency for crash recovery. ScyllaDB, at the end of the day, is a persistent database. So although you can disable the commit log if you so would like, ScyllaDB is often run as a persistent database, so we always want to ensure that your writes are persisted to disk before they are considered successful. Either way, as you keep writing to the database, eventually your main table, that in-memory data structure I just spoke about, will eventually get full, and we need to flush its contents to disk. And as part of this flush, this results in an SS table. Newer writes will then go to a different main table, and this process will repeat over and over again over time. All right? So this is how basically writes work in ScyllaDB. One way, given that flow I just explained it, is one way for you to actually ensure read consistency, therefore, is to simply merge data from your existing SS tables stored on disk with the contents in your main table. And this approach actually works fine, but there's one important problem with it. It is super slow. If every read we need to service our requests needs to potentially touch multiple SS tables on disk, then there's no way to overcome it. Your tail latencies would be badly affected. So we need to find a better way. We need a cache. And the natural question that comes after is, okay, so how do we implement this cache? Well, traditionally, the most traditional way, which is what you will find in most databases out there, would simply be to use a buffer cache, which is basically relying on the Linux page cache, where we cache the pages we read from SS tables stored on disk. And because the typical default Linux page size is often 4 kilobytes, that's the granularity we would basically store in RAM. So every page would have in RAM would have a size of 4 kilobytes. But there's one problem with this approach. It is very prone to memory wastage. For example, if we cache an entire 4 kilobytes page, but our read only requires a single 300 bytes row, we've just lost an important chunk of memory. Database users often store data sets much larger than RAM, which means that access locality is also very unlikely. Access locality, in case you are not familiar with this term, is basically the likelihood that of successful read operations actually being in your cache. So if you end up in a situation where you don't have access locality, you have bad latencies. Another problem that the buffered cache does not address is basically negative caching. If you don't have a key you are after, we would need to cache an entire page simply to indicate its absence. If the page gets evicted and a subsequent read requires reading from the same buffer, then we have no choice but going through disk again. And this again is very bad for latencies. Because ScyllaDB reads may require touching over multiple SS tables, reading through a single or multiple rows may require actually caching several SS table buffers. And this basically pronounces the memory waste remark. Another reason why not to use the Linux page cache is that this also introduces lots of CPU overhead. Think about it this way: databases are made almost to persist your data. And SS tables, the SS table format that is stored on disk is optimized for saving disk space, not really to for read speed. In other words, the data stored on disk follows a different format than the one we use to actually service clients, and caching their contents further even reduce the effective memory you have available, which introduces parsing overhead. Um, yeah, so this is basically what I just discussed, and my dog is now barking. Um, he should probably stop shortly. And the last and final reason not to use the Linux page cache is, of course, compactions. Um, compactions are basically this thing that those LSM databases, ScyllaDB included, have that's actually running all the time. And because compactions effectively updates references to the underlying files that you have on disk, every time compactions happen, it basically invalidates and evicts the contents of your buffer cache prematurely, which at the end of the day affects your read performance. So, naturally, given all those reasons, we built our own read through cache. Data not present in the cache goes to disk only once. We populate the cache, and subsequent access doesn't require touching the disk again, thus avoiding the host of problems which I just described. Um, so let's now talk about how the ScyllaDB cache structure works. It's basically implemented as an object cache optimized for very little CPU overhead. Like main tables, our object cache stores rows instead of particular files or chunk of files present on disk. This is great because if you have a given row present in multiple SS tables, ScyllaDB will hold in memory only the conciliated result, the conciliated row in memory, which helps preventing the memory waste I discussed earlier. Um, One particular characteristic of ScyllaDB's cache is that it is also dynamically sized. When you start ScyllaDB, by default, it will reserve most of the host memory for itself and leave only a small portion for the OS to function. We, in fact, often joke that ScyllaDB is a very greedy fellow. Um, Either way, the cache by default uses all freely available memory, but sometimes we may need to shrink your cache when other components of ScyllaDB require additional RAM. For example, let's assume that your main tables are unable to be flushed in a timely manner because, I don't know, you have a disk bottleneck somewhere. We can't simply stop accepting your writes. So what we do is we create other main tables so your write traffic can continue to basically blast your database, and as your write, as basically the size of your main tables grows, we start shrinking your cache slowly. And then once the situation is resolved, then the cache gets back dynamically gets back to its optimal size. So in reality, when you look at the diagram in the previous slide, because of ScyllaDB shard per core architecture, where this is how you should actually imagine the previous diagram. Um, so our shared per core architecture basically ensures that each CPU gets its own dedicated pool of resources. What this means is that each CPU gets its own portion of SS tables, main tables, and RAM, and each CPU's cache gets dynamically allocated depending on your workload, depending on how your access patterns are actually distributed, whether you have imbalances, and so forth. Shard per core allow us to have complex operations on data without, having to deal with real concurrency. which is something we would face if we used things like multi-threading and accessing data from multiple CPUs for shared access. We don't have to use locks, which avoid lock contention, nor need to implement complex lock-free algorithms. So in a way, shared per core actually simplifies our cache development. For example, when we have a read, it can access simply cache and main table local to that CPU. And by doing that, you have a consistent view on both. And again, this is basically achieved without involving any synchronization mechanisms. But not everything is like flowers when we talk about caching in databases. For example, ScyllaDB has a very rich data model. Yeah. And naturally, implementing the semantics of our data model in our role-based cache did not came free of some of those challenges. One particular challenge I'd like to exemplify here is basically handling range queries. For example, select all the data from a given user after a given date, or delete all data after a given period of time. Um, how can we basically represent those open-ended queries, which we call range queries, in the cache? Because if you look into the query here, the query is basically asking for everything larger than 2. How do we know whether we hold the entire range in memory or not? So ScyllaDB's cache is basically designed to handle this case. We store information about what we call range continuity, indicating that if a given range in the cache is complete, there's no need for us to go to the disk and check whether we have additional data. If the range is incomplete, then we inevitably have to go to the disk so we can mark this range as complete. All right. Um, Range deletes, which is the same thing have just shown, but for deletions, also require special handling. In LSM databases like ScyllaDB, a delete is actually a write of a marker, which we call tombstone. Because remember, as a distributed database, in order to ensure very low latency, the actual deletion of your data happens lazily after you actually delete data. This happens via compaction, but this is not really relevant to what we are discussing here today about caching. Therefore, whenever you delete data, we also store tombstones in the cache along with its range continuity information, and we have to update it as needed in case any subsequent write comes in and change the state of data as it is stored in the cache. For example, if we delete everything that's higher than 2, then we basically store a range continuity plus a tombstone, so we know everything is deleted. But if another write comes in and stores data, I don't know, into 10,000, then what we need to do is basically, okay, so we have a tombstone between 2 to 999, 9, and the row at 10,000 is actually lives and is the end of this key. So we basically address those corner cases. And lastly, one of the main disadvantages when you are working with a read-through approach is that it may lead to, infrequent or never accessed data, effectively evicting important items from your cache. Depending on the workload you are running, you don't want really to evict items from your cache because this may, at the end of the day, hurt your latencies. So ScyllaDB provides one query extension, which we call as bypass cache, to support those use cases where code reads or heavy scans of data simply tell the database that the result of this read should never be populated to its cache, which sort of prevent the situation known as cache trashing, which is when you are constantly evicting and populating items on your cache. and in turn helps you with your performance. All right. So to summarize what we've discussed today, ScyllaDB has a fast read-through cache, which provides efficient access and low-effort maintenance. It takes care of consistency guarantees as required by the protocol, and it addresses all the complexities within the data and query models that ScyllaDB requires to operate as a highly available distributed NoSQL database. All right. So this is what I had to present. I hope you've liked it and learned something new.
And I'm going to be talking about the trade-offs involved with in-memory data stores. We'll be specifically focusing on Memcached because that is my core competency. And my background is also in CDNs. I worked for Fastly for quite a while and did caching and database administration and SRE stuff at various companies. And now I work with I am Cache Forage, and we do consulting work for Memcached. I help other companies run the system, and they help sponsor the project in return, and that's great. So to get started, I want to first define Memcached as a tool. It is not something that you throw in front, not middleware. It is not something you throw in front of your application. It is a in-memory look-aside key value store. It is as a tool. It is like a library that you use to help scale, help overcome performance problems, or deal with cost. Um, and this flexibility allows you to customize it to fit your exact needs, what you actually need day to day. And in case you're not familiar with Memcached, and even if you are, we'll start with some of the basic capabilities. And I really want to boil this down to the highest level categories as possible for the way we do commands, because you might be more familiar with some other in-memory data stores, which are kind of kitchen sink focus. They can kind of do everything. And since we are a distributed uh, ephemeral cache data store, we have a much more focused set of commands, and we'll keep discussing that to understand why coming up. But broadly, uh, we just have fetchers. You have get in the original protocol, get, gats, gats. So this is the basic protocol that we have for Memcached. These literally just text that says this and then a key, and then you've got you're off to the races. We have mutator commands, which is set. That's how you get the actual data into your cache. This also has different variations of append, prepend, cas, touch, delete, and arithmetic commands, which is kind of our one little data type for now, which is just increment or decrement, and for maintaining counters and rate limiters. We also have a high-level concept that is bolted onto some of these protocol commands called compare and swap, or CAS. It is just an extra numerical ID, and if it allows you to say, okay, I've fetched a value from cache, and if that cache value hasn't changed since the last time I looked at it, then let me update the value again. And that lets a couple different clients kind of race and ensure that the latest update actually wins. And it can also build different capabilities on top of that, like locking systems. And finally, the method of distribution was not primary, secondary. We're not by default replicated. It is client focused, which means your client software or whatever you're using to access Memcached takes the key, turns it into a hash value, and then distributes that hash value using consistent hashing across the your list of servers. And this is done because the primary point of Memcached is to give you a wide cache, to let you use as much memory as possible, to get as wide of a cache as possible, and get that nice long tail of data in there and help you get your P99s up nice and high. Uh, so the data you actually store in Memcached, it doesn't really look at it at all, except for the case of Inker and Decker, obviously, where we need to look at that number, then increment it or decrement it. The values are just flat bytes. We have a little bit of metadata outside of that. So we have a 32-bit flags that are part of the protocol, but not actually part of the value. So you can use this to describe via your client, like, is these blob that I just stored compressed? Is it encoded with chords or message pack or JSON, and kind of give your client a little extra hint from when it's fetching the data back. Or if it is a specialized data like a tombstone or that sort of thing. And then we have the 64-bit CAS ID, and as I said, the raw value. The stuff that you can use this for is pretty much anything. So Felipe talked a lot about uh, row caches and things that are directly connected to the database, but Memcached is just a key value store. So this could be the result. You can store the result of complex queries. I'm going to fetch from rows 1 through 10 from table A and more rows from table B, and I'm going to put them all together into one value, and I'm going to store that in a Memcached. And then when I come back later, I'm going to fetch one key and get all this complex stuff back, and not have to query the database for all this stuff. And it could also be the result of like API calls. I see this quite a lot in these cloudy times, where you'll have your service will have a dependency on something external, an API call out to somewhere else, and you might not necessarily need to hit that same API for the same set of arguments. So you could say like, oh, I'm going to translate a string with this external service. You don't need to ask that external service for the same translation of the same string every time. It's going to be the same. So you could cache the results of that and save yourself some time and money. So now that I've defined this, what Memcached is on a high level and where it helps you as a tool, I want to take a quick second to step back and talk about why these commands are the way they are. And this is mostly because of Memcached is a distributed first project versus as another in-memory data store, which might be single instance first. And I want to talk about how that differs. So primarily, if you're starting from a single instance focused data store, you can have lots of stuff. You can search and sort keys. You can throw in locking systems and all kinds of commands and queries and stuff, and then you can replicate the whole thing to another instance, and then you get nice failover, and you can scale that up by bigger and bigger instances. Or you can isolate data where we have stuff from application A and then application sub B, and it goes in different servers, and you kind of scale it out that way a little bit, but it's not exactly clean for scaling out, but it does allow you to have that complexity. Now for Memcached, since we are assuming from the start that we are a distributed system and that in order to add more cache to a pool of servers, you just add another pool and just let it go. We can't have commands that are fetching keys across from each other, because then all the servers will have to talk to each other, and you'll end up losing a lot of that performance. And it also greatly increases the complexity of the cache invalidation, which we will talk about shortly. But that gives you the idea of why things are the way they are. Like we are all of our commands are focused on distributed first, and generally O1 or ON or O sub n for scaling complexity. So that you really can't get yourself in trouble no matter what command you're using with Memcached. So one of the biggest complications with data caching is cache invalidation. You've probably heard that one of the hardest things in computer science, cache invalidation and naming things and off by one errors. So we have a base innovation for this that we'll get to later. But I just wanted to take a breather to point out that yes, it is legitimately hard. And CDNs are actually even harder. I added this at the last minute here, but I did used to work for Fastly, and we had a global cache purge system to kind of keep your data in sync across the entire planet, and that was some very smart people. It took quite a while to get that working very quickly. The primary tools you use in Memcached for cache invalidation are setting a time to live on an object. So if you say set it and you say it'll live for 30 seconds, the cache entry will obviously disappear after 30 seconds. You'll have to fetch it from the database again. It'll get updated that way. You can delete them actively. So if your database, you update your row in your database, and then you go and delete the data from cache. I've seen there's some old systems that actually bundle this with their database. So if you have queries that go to your database and then plugins on that side somewhere that says, okay, I've when this the data updates, go and run a hook and go delete this thing in Memcached. I don't think people typically do that anymore, but for quite a while it was pretty popular. And then you can set something directly. You can overwrite the value with the latest data. And so what we bring to this table is the simplification, is this distributed first nature, and where a key will only live in one server in a pool, meaning you delete it or you set it, and you can go, you know exactly where that key is. You don't have to broadcast anything, and that does actually help simplify stuff. But there are different ways that this gets complicated. We're not going to have time to get into that today. Uh, but you have to keep in mind that servers can fail, you can have network issues, and those things can cause you to miss cache invalidations, and then your data might be stale. So you might end up having to use something like Kafka to route your deletes and make sure they actually get executed, depending on what your client is or how important that is. So databases have been better. We don't need to cache absolutely everything anymore. I am fairly old. I've been doing this a long time. When these distributed caches were new, we were in a position where there just wasn't a lot of money to go around. The databases were fairly slow. They're running on magnetic media, spinning Rust. We didn't even necessarily even have good RAID controllers to speed that all up, or tons of memory in our databases. And so you typically had to run pretty much everything through your look-aside cache outside of MySQL or Postgres or whatnot. And these days, you kind of don't have to. Scylla has its own cache, obviously, but also you have very fast flash drives, larger servers, the more optimized databases, which can do point queries much quicker. You don't have a lot of you don't necessarily have the SQL overhead, or that's been optimized. Um, so ideally, when you're looking at Memcached, you're saying, what can I get for the biggest bang for my buck? What can I do? Since I do have to make a modification to my application, what is the smallest thing I can do for the biggest reward? Where should I put this? Where should I be looking in my stack for implementing this? And generally, the higher up, the better. So these days, gRPC and some similar RPC protocols are very popular, but they're also very heavyweight. They're if you're making queries for very small data, like I just want a row from a database, having to do gRPC, wrapping all that up, can actually use quite a lot of CPU. Compared to Memcached, clients and protocol, it can be 10 to 100 times more CPU and latency to fetch something through gRPC than through Memcached. And obviously, if you're using gRPC to request like an API endpoint, which is going off and doing other things for 300 milliseconds, fetching a bunch of stuff from a database and then coming back, then that gRPC overhead isn't huge. But if you're fetching like a post or a thread or someone's username or something, and you can't necessarily batch it and batch a bunch of these stuff into one gRPC query, then you're going to be burning lots of CPU in your front end for fetching very little data. And so it's a good place to put Memcached right there. And if you need to go down a layer below that, the database drivers are also fairly CPU intensive. They're these in SQL cases and in Scilla cases, they're much more complicated than Memcached is. So if you can avoid even going through the database driver at all, that gives you extra CPU back, it gives you extra scaling back. And if you are covering, like if your look-aside cache is outside your database, is outside your gRPC calls, you can use it for dealing with like very bursty traffic, since we're a much more efficient system. And as I said earlier, externally hosted API calls can be expensive. You can either be spending money for each of these calls, like every time you need to translate a string or turn an image into a thumbnail or something, and times where you can cache that can help a lot. And even in the cloud, like most of these databases like DynamoDB they're just hosted APIs basically. So you're just kind of throwing this in front of that and trying to move on with your day. And there's quite a lot of data that doesn't necessarily need to be in a database at all. Um, so data that you're generating daily, that is, or hourly, or stats counters on things for lots of stuff with machine learning and training data, not necessarily has to be in a database. And also databases aren't that great at just overwriting everything all the time. And so you might have this big old data load, and you instead of putting that into databases or expensive API database databases, you can do replicated caches and say, okay, I've got one pool of servers 123 here, and another pool of servers 123 in another availability zone or another data center, and you write this data twice, and so you have some resiliency to loss. But you're avoiding the entire cost of the database. And of course, if you can, just throw the thing in a CDN and take a nap. And then just to wrap this up, or start to wrap this up, I guess, it's good to, now that you've kind of have an idea of what the commands are and where to put it in place, like what else does Memcached bring to the table, or these in-memory data stores even, because most of them are pretty similar for these kinds of benefits. What do they bring to the table for the best the best benefit that you're going to get here? Like what is it you're actually getting from moving it out of your database? And obviously, I've said before, the wide cache multiple times, so getting lots and lots of RAM available or disk space available to the cache, gets a nice long tail. That's the distributed nature. But the daemon themselves, they'll have a very high request rate per core. Um, and so Scylla recommends something like 12,500 queries per CPU core, and Memcached can do a lot higher than that, depending on the data, depending on the amount of batching you can do. So if you can fetch 4 or 5 keys at once, the performance is even higher. It goes even higher. So you can really soak, like if you have like a news site, or your front page is very popular, or you have a news event or a hot thread on a social media site, you can kind of absorb that. And we can also are very fast at deleting data. Is kind of a weird one, but like actually removing things from databases, that none of them like that. No database I've ever worked with has really enjoyed having lots and lots of stuff deleted from it. 'Cause they have to deal with Tombstone, they have to touch, they have to write stuff to the disk. It's not all that fast. We can delete things. We can expire things. Forgetting things is a feature for Memcached. We can also overwrite anything in memory pretty much instantly. And if there's nothing there, the misses are very fast. So if you're fetching something from a database that's not necessarily there, it might have to calculate a Bloom filter and hash the data value a couple different ways, and then walk through a couple different caches and see if something's there or not. And then it could, if in possibly in Scylla's case, have a negative cache to speed that up going forward, but it's still a little bit more complex than if you're just asking Memcached and it's not there. It might not be there. Or if you can put an entry in Memcached, which is a negative cache for something that isn't in the database. And then talking about growth, we have this built-in proxy now. I'm not going to have time to go into it today, but the docs are there. You can go ahead and get started, and you can reach out if you're curious about it. This lets you run a simple client, and you can run as a sidecar directly hosted on your application. And then instead of having your client manage the pool of servers and consistent hashing and all that, you let the proxy do it for you. We can replicate between data and keys between pools of servers. You can do dynamic scripting to do some custom work. And if you have like some certain large data that you don't want to be routing the hit rate of your main cache pool, you can split that off and have by key prefix or some other measure be splitting off in the different logical pools of cache. And there's lots of potential from there. We're just trying to figure out what we can do with it now. So for the rest of this, I want to pivot into some modern cache primitives. We discussed the basic features of Memcached and various approaches of when and where to use it. All of that's been the same for decades at this point. So I talked about MySQL and MyAssignment and ODB and all that stuff back in the day, and Memcached has been largely unchanged since then. We've added a binary protocol which tried to modernize this a bit quite a while ago, but didn't really catch on as much. So the original protocol is nice and simple, but it did have some drawbacks, and we have iterated on it. And this is a addition to the simple text protocol. I call it the meta text protocol. You can actually run the old commands and new commands on the same connection. So if you're migrating, you can just test, like I've got gets and then I've got metagates, and you can all mix them all in the same connection. It all works just fine. And notice we're using the singular now. We had fetchers and mutators in the first slide. Now we have fetcher and mutator and arithmetic. These are MG. MS, MA, and you fetch your key, and you have flags, and the flags describe what data you want to get or want to affect in your command. And just as before, we had compare and swap, but now it works on every command for every situation. And this encompasses all the previous protocols, all the features. So anything you can do in the original protocol, you can do in the meta protocol. Anything you can do in the beta and the beta binary protocol, you can do with the meta protocol, and then more. Plus, we can now add things to it by adding new flags and tokens without breaking backwards compatibility with cold clients. And this has been around for a while. I say new, modern, but we wrote this thing in 2019, and although we have been revising it slightly here and there. And next, we'll go over something that the original protocol struggles with, and which was now improved with this meta protocol. I think most people are familiar with the idea of stampedes and stampeding herds, where you have a cache miss or a whole bunch of clients come in at once, and they all drop back to your database all at the same time, and you run the same query or similar queries. And depending on how your database is architected, they can use lots of resources, it takes lots of time, or you're just clobbering, you're just wasting resources fetching all this stuff from the database and writing the key back to the cache a million times in a row. With the original protocol, we were able to get around this a little bit by adding a lock key. So if you get a key miss, and then you go and add a secondary key. And if you succeed in doing that, your client wins. It gets to go to the database, gets to update the cache, um, and uh, and move on. I think someone's asking, is this C, C++? Are we talking Rust back in here for the cache platform? The Memcached is C. Uh, it's a very old project, and frankly, if we rewrote it in Rust, it would be a different thing. But it is very old, very stable, very slow moving. So it's not as big of a deal as you'd think. And anyway, back to stampeding herds, you'll see that you're kind of going around and around. You have extra back and forth. These charts look kind of messy here, and you have that secondary key, which isn't necessarily what you want. With the meta protocol, we have these extra keys, extra flags, and so we can say when you fetch a key, we have this little n, this n flag here. So we have mg key v. V means give me the value back. Capital N means if this key did not exist when I went to fetch it. Um, initialize an empty value with a 30-second time to live. We have our n30 there. And then if this cache client, this request did create this key because it is missing, so it misses it, there's nothing there, you get a miss, it automatically creates this empty value atomically, and then it sends back to the client a special flag, a W. And that says to this client, hey, you won the race, it's your job to go update this data. And I think someone in the chat was asking about leases, and this is very similar to a lease. So you just won this lease, and then you write the key back to the cache, and you move on. We have this extends into similar concepts, like if you're familiar with HTTP's features, stale while validate, stale while error. So we have a different flag, and here we're fetching an mg key v for value, t for getting the remaining time to live on this object, and then we have r, capital R, and 30, which means if the time to live on this object is below 30 seconds, then get a lease to recache this object. And so we see here in our response, we get our value back, the length of the value. We see that there's 25 seconds remaining in the TTL, and that we won. And so now this cache client will go back and refresh the data from the database and set the data back to the key. And in this case, no clients see a miss. You don't have to wait for the database or wait for that remote API call to the translation service, which is very slow. Your clients are always getting something fresh from the cache, and you can do this refresh asynchronously. So your client says, okay, I've got the data back. The data's still there. This data's still good. Other clients will also see this. Will get like a Z flag back, which says this data is good but stale. And so you can use that data, and then the first client can go asynchronously refresh from your database or your API and put it back in the cache, and you move on. And this is all atomic and minimal round trips. And so the last concept, and the most recent one, the most modern, is improving cache consistency with CAS overrides. So I mentioned before that if we have these CAS IDs, which for Memcached is just a sequence of numbers that starts at like 1. So when you set something in Memcached, that thing will automatically get a CAS ID of 1, and then the next one gets 2, and then if you update the same key, it'll get 3, and then that's just kind of a global value. And so that means whenever you fetch something from Memcached, if you also fetch the CAS ID, you can then use that CAS ID to set back the new value only if it hadn't changed in the meantime. This is good for some forms of consistency and some forms of locking and then that sort of thing, but it's not so great for ensuring consistency or being able to check consistency later if you're curious, or if you have multiple cache pools, or if you want to check if your cache is consistent with the database occasionally. So what we have now is CAS overrides, where since we have the meta protocol and we are much more flexible for what arguments we can add with the command, we have this E flag, which just lets you specify a number, and the number can be from a database row. Some databases have a row version. It could be a timestamp if you're scary, or if you have nice atomic clocks. It could be a hybrid logical clock. You can look that up on your own. Which is slightly less scary, a little bit of fiddling, but is generally pretty safe. Or any other value that you have that might tightly couple your data, your API response to your cache. And as a quick example here, we have our ms command, which is our set, and we ms test for a 2-byte value, and we give it a 73 for the force CAS, and it succeeds there. And then when we fetch it back, we get that value back, and we get the CAS that we set instead of the one automatically assigned by the server. And then the next time we run an MS, we can say, okay, my CAS was 73. I want to set the new one because the new version number or the time is now 90, and we all succeed and move on. And this lets you expand into multiple cache pool consistency. So now we have some way of saying if we have pools in availability zone A, availability zone B, or different data centers. Obviously, I said earlier that the CAS IDs are per server. They are incrementing numbers. So each Memcached has its own set of CAS IDs. And so if we're trying to replicate our cache between between data centers or AZs, we have no way of ensuring that the data in A and B match, or being able to check that later, or do any kind of reconciliation or offline reconciliation. But with this, you can, because now we're controlling what the value is for this CAS, for this extra ID, and you can check that later. And the nice thing is that it is just our standard CAS, so all of our commands that worked with CAS before in the original protocol or in the meta protocol all work the same way with this. And if you have ideas for this or anything similar, I'd love to hear about it. We have a Discord for Memcached.